Okay, it's 2:02. Let's get started. Hello, welcome everyone to Ask Seminar series. I'm John, the seminar coordinator. So I'll be moderating the seminar with Kathy Medley, our communication specialist. And also join us is our director, Nas Peter, and he will be introducing the speaker. Just so you know that the seminar is being recorded and we will post the recording on our YouTube channel. And we encourage you to bring up any questions you may have after the presentation. You can do so by just muting yourself and speak out. Or if you don't have a mic, please feel free to chat us the questions and we'll read them out. So before the speaker gets started, I will hand this ball to our director, Nas Peter. So Nas Peter, please go ahead.
Thank you very much, John, and thanks for joining today's ESSEC seminar, and special thanks to our speaker, Jessica Lundquist, who is a professor in the Department of Civil and Environmental Engineering at the University of Washington. Jessica earned her bachelor's from UC Davis and both her master's and her PhD from Scripps at the University of San Diego, and was focusing on mountain streamflow. Jessica has received numerous honors from AGU and also from AMS. By her informal self-introduction, her title is Snow Professor. So she will be speaking to us today about snow and snow in the mountains in particular. As an avid skier, I have a keen interest in snow in the mountains, but it is important also for much more serious issues. There are, in many areas of the Earth, there are populations that rely on the snowpack in the mountains for their water supply. So there are serious ramifications of our ability to estimate the water content in the snowpack, and it's a really, really pesky problem. And that is, I think, what Jessica will walk us through today. So I really look forward to hearing about that. The floor is yours.
Right. Thank you. Thank you so much for that kind introduction. And just a fun fact, the ESSEC seminar, I was Googling to try to find the link, and it got my name, ESSIC, Jessica. I have the ESSEC seminar in the middle of my name. I got all of my email. It was a very bad search term to use for me personally. But moving on, today I'll talk about patterns in the peaks, connecting mountain snow and streamflow. And here you see a picture from the top of the Crystal Mountain Ski Resort on a nice day with Mount Rainier, and draining from Mount Rainier is the White River. For people trying to decide if they want to stay on the seminar or not, I'll give you the outline of everything we're going to talk about. You can decide whether it's what you signed up for. So first, mountain snow equals summer water. Mountain snow is highly variable and tricky to measure. Topography shapes meteorology from precipitation to the energy available to melt the snow. Topography leads to repeatable patterns, which we can observe with recent technology. But rather than being overwhelmed by the variability in the mountains, we want to think about coherent patterns with patterns at multiple scales and how we can use this coherence to our advantage. I will also, at the end, because I get this question a lot, tell you which snow products you should use for mountain snow. So let's start. As Lars mentioned, mountains are the water towers of the world. They store water as snow, but it's an outstanding question of how much is there. So this is a graphic right here. The red coloring is showing what Steve Margulis and the Jet Propulsion Laboratory in a recent snow mission proposal called the Snow Human Nexus regions. These are 3 billion people who live in watersheds downstream of mass snow area. Basically, the mountains store water as snow. Here's a watercolor from Matthew Sturm. And right here is a picture of Lake Mead, Colorado in the Western US, which has water for 7 states, but never enough of it. So how much water is in these mountains? It's surprising that current estimates of snow storage, which we call snow water equivalent or SWE, in the global mountains, They range by, a factor of 6 to a factor of 10, just to try to put these quantities in, if you don't think in kilometers cubed, that's 0.8 million acre feet, whereas a million acre feet is how many millions of football fields we would fill with a foot of water. So this is a lot of water and a huge amount of uncertainty in these different mountain ranges. So what I'm going to talk to you today is how can we get at this? And how can we get at this by thinking about the hydrologic cycle? So this is a picture from the USGS, and you can see I flipped it around because I live on the West Coast and I see water coming from the West Coast. For those of you on the East Coast, you can flip it around the original way. We'll be talking about precipitation, which is rainfall plus snowfall. That becomes snow storage, which becomes streamflow. All right. So here you see is a recent paper, well, 2020, it's 5 years old paper, by Colleen Mortimer in the cryosphere. And what you're seeing here is a map of Northern Hemisphere snow water equivalent. Also use the word SWE, which basically is the depth of water you get if all the snow melted. And this is the mean for January, February, and March from 2003 to 2010. And up here in the upper left-hand corner is the mean of a number of different reanalysis products, the mean of the glob snow product, which is based on remote sensing, and the mean of 2 different NASA remote sensing products. All right, so now I live in the Western US, and so anyone who's ever visited out here in the winter, whenever I look at one of these global products, I always want to do a fact check. Where does it look where I live? And so if I go zoom into places I've been, it says the reanalysis mean, which is the most trustworthy, says there's about 20 centimeters of snow in Washington, 2 centimeters of snow in California, and 8 centimeters of snow in Colorado. So anybody who's been out here, do you detect something maybe terribly wrong? Let's just do a field check. So here I am in Washington. So 20 centimeters of snow water equivalent. That's how much water you get. So snow water equivalent is the depth of the snow times the density, which is about 40%. So this would say we have about 50 centimeters of snow depth. So here we are last winter. All the students from my class go up to Snoqualmie Pass in Washington. This is kind of a below average year. Snoqualmie is not very high. If you've ever been out here, it's where I-90 goes over the pass, across the middle of the Cascades. And we dig. And here we are. We fit in the snow pit. Here's an earlier year that was more typical. We kind of really fit in the snow pit. And what you can see here is that on February 2025, we have more than 160 centimeters of snow, which is about 3 times the mean reanalysis estimate. And just for reference, I'm 160 centimeters tall. So, this is pretty typical for how much snow we see in Washington. And this isn't telling us how much snow. So what should we do? When you look across the Western US, you can see that out here, we have a lot of mountain peaks and a lot of sharp contrasts in precipitation. So we like to joke that, here in Washington, University of Washington, we're the purple color. And so we get really the only purple in the color bar of precipitation. That we get 100 inches, 8.3 feet, 2.5 meters of water each year up here. Also, the mountains of Colorado, 1 meter, 40 inches, 3.3 feet. You can also see that the contrast is we have desert right next to this. Whereas on the eastern side of the US, the variation is much smoother. You can also see that this variation in space also happens in time. In the Western US, most precipitation falls in the winter, and summers are dry. So here's Seattle. This is plot across the US. And what you see in each one of these, so this is for Seattle, you see month of year, January, March, May, November, how much inches of water. And what you can see is right now we're going into our rainy season, but that in the summer, it really almost never rains here. And if you look at San Francisco, California, it really doesn't rain in the summer in California. In contrast, the East Coast rains pretty uniformly year round. So out here, because summers are so dry, we need the snow water for agriculture. Despite this winter precip, So here's the preset for Seattle and San Francisco. You can actually see that Streamflow peaks in the spring and summer. So because of the snow water, we actually are getting water when we need it most for agriculture. And this is just a nice plot of all over the US, the normal distribution of runoff by month from Langbein and Wells. So over 50% of Western US water supply comes from mountain snow. This is a picture out my airplane window looking at Yosemite National Park. And the Western US, just to summarize, gets very little summer rain. The volume of snow, so here's your snow accumulation, determines the total volume of runoff from the snow. And that timing allows us to predict summer runoff. And just to iterate, that snow water supports agriculture. So due to this importance, going back long ago, back in the early 1900s, and by the 1950s, a team of snow surveyors, currently run primarily by the US Department of Agriculture, Natural Resource Conservation Service, but the snow surveyors went out and took basically a pole. So you can see this guy takes the pole, puts it in the water, puts it in the snow, pulls it out, fills it with snow, and weighs it. This is a little spring scale right here. He's weighing the water equivalent in the snowpack. And they go out on these snow courses and they just measure at an index site every year. And since the 1950s, the snow surveys have successfully forecasted streamflow from these snow observations. So here on the x-axis here from this is a paper in 1953, you can see they're forecasting streamflow, runoff, and 1,000 of acre feet based on this measurement of the snow storage right here on the y-axis. And you can see they're doing the forecast with a 10% air bound. So the regression from the snow survey is generally accurate to within 10%. So to me, this gives it a bit of a disconnect, right? There's this historic forecasting success of being able to take an index measurement of 1 point of snow, predict how much stream flow there's having. And then when you go and you look and say, what is the volume of snow in the mountains, our estimates vary by a factor of 6. So what is the disconnect here? In the 1950s, stream flows predicted from snow measured by humans at just a few points, with usually less than 10% air. And here is a recent paper by Feng et al. 2023 in the cryosphere that shows the average total amount of snow in the Western US ranges from 30 to 180 cubic kilometers. These values are enough to fill Lake Mead 5 times or to not fill it at all, right? But you clearly can't actually manage Lake Mead with a degree of uncertainty here. So how did this range get so large? So if you look at a variety of co-located gauges, they can vary by a factor of 2 for snowfall. You can also see, this is a photo by Nick Wayand, who says that, conditions that are good for snow are bad for instrumentation. That's the site we put out. And this is from a paper by Roy Rasmussen in the plains of Colorado, where they put out every instrument they could find next to each other. They should have measured the same thing, and they varied quite a bit. You can also see that where the mountains are, the mountains block the radar. So we don't see rainfall or snowfall in the radar measurements. Also, if you go out, these are some pictures from Matthew Sturm in the Arctic, but the same thing will happen if you go in the mountain. These are just a few feet apart from each other, right? You dig one hole and you find that, it's twice as deep as the humans are. Dig another hole and it's, barely as deep as your mittens or your shoes. This is a paper by Merrimee et al., where they went and they did snow surveys all around these snow-tell sites, which are index sites that they're using to predict the snow water equivalent. And you could see that even around one site, the snow you measure at different locations, if you were to move that measurement slightly, varies from a factor of 2 to a factor of 4, depending where you are. These are also some photos from the Snow X Field campaign in Grand Mesa, where one snow pit you dig, you could fit every person on your field campaign. And the other one is so shallow. This is Carrie Voyevich decided to build a snow structure because she got done with her digging so much faster than the people over here. Satellites also have a lot of potential for measuring snow. But in cases of deep snow, wet snow, and forests, current sensors really have trouble. Deep, wet, and or forested actually describes most of our mountains. So you can see here that that right now KU band is good in shallow snow depth without a lot of forest. C band gets you to a little bit higher, L band goes a little bit higher. And as you get to the Pacific Northwest, really nothing currently up in the sky is measuring the amount of snow we have. So what can we do? So we can check streamflow volume. So here's the range of snow from a number of products that's presented in Fang et al. 2023. And here is a graphic from Jane et al. 2005 of the major snow-fed river basins of the Western US. So this is the domain for the Western US that Fang et al. Used for her estimates of total average snow volume. And let's just look up what is the total average runoff from all of these rivers. So if we look this up, this is courtesy of Wikipedia and Google AI, so take it with a grain of salt, but I think it's a fair estimate. Columbia River, 244 cubic kilometers of runoff. Sacramento, San Joaquin, 7 cubic kilometers. Upper Colorado Basin, 18 cubic kilometers, for a total of 270 cubic kilometers of runoff on an average year. Let's assume 50% of that average runoff comes from snow. So we take half of that, 135 cubic kilometers, gives us this line right here. Remember that picture right here, 135 cubic kilometers. So remember that picture at the beginning that says we need rainwater stored as snow that becomes our runoff. So really, it looks like to give you the runoff, only these products up here at the top are likely to be reasonable in the volume of SWE for this region. Now, looking at all that, you might say, okay, this is completely understandable why we have this uncertainty, right? Snow is hard to measure. It's extremely variable in space and time. The instruments break. But at the same time, with all of these challenges, how and why can snow surveyors make this work? So this is also a view of Mount Rainier. So in thinking about this, something that struck me is my son was learning music, and he's looking at the music, and he's telling his music teacher, like, how on earth can anyone figure this out, right? This is way too much. How can we figure out all these notes on the piano on mud? And the music teacher says, well, really, your brain stops processing all of these as individual notes. Your brain starts thinking these as chords, scales, intervals. The grouping of notes are patterns, and your fingers remember the pattern. And so let's start thinking about patterns. So if you play piano or any type of music, you might have noticed that what I put up there says the snow glows white on the mountain tonight from Disney's Frozen. And let's look for patterns in the mountains that create organization and structure. Once you start thinking about it that way, repeating spatial patterns, especially in mountains and snow, are ubiquitous. This is from a paper by Matthew Sturm and Anna Wagner in 2010. And what you see on the left, this is the Mountain of the Holy Cross in Colorado in the United States, painted in 1875 by Thomas Moran. And here's an insert of a photo from 1873, so you could tell he's painting it pretty realistically, as well as a picture in 2004 of the same location. This mountain cross repeats year after year, and people actually use it to document timing of streamflow. I put this up at a conference, and Eric Sproles sent me an email with a photo right here that was taken by Mike Roberts. And Eric wrote, in this picture, the butterfly is in the Pintler Range. And Mike says that the ranchers say that when the wings separate, there's something like 2 weeks of good water yet left. It's not just in the Western US. There's actually a term in Japanese called yukigata. And yukigata means the shape of the lingering snow on the mountainside. And you can actually sign up for a yukigata tour in Japan and go see the shapes of the mountains. I was also in the Alps recently, and they said that there also are shapes in the Alps that people use to predict things. So why are there such repeatable patterns? In the West, the story starts over the Pacific. We start with water in the Pacific Ocean, And the storms really consistently come from the same direction. So we have, warm ocean water evaporates in the tropics and hits the West Coast, often in narrow plumes of moisture, but they're all pretty much from the southwest wind direction. These plumes of moisture interact with the topography in fairly predictable ways. So this is a paper by Alexander et al. 2015, and they're showing moisture pathways. So basically, the mountains block, deflect, or extract precipitation. And so there are like known paths through the mountains. These are the low points. And this is a figure from Chu et al. 2011 showing precipitation patterns that here you can see that all the mountains get wet together, north versus south, that are repeatable. Similar places are wet at the same time. And while individual storms may vary, the bulk of the seasonal snowpack is made up by similar types of storms with similar trajectories that end up depositing similar patterns of snow. And as long as the wind directions during snowfall are consistent, we expect snow patterns to repeat at actually very fine spatial scales. So here's topography, and you're going to get deposition in the depressions, erosion at the crust, and deposition in the lee of a crest. And multiple papers have found snow patterns at times near peak snowpack repeat interannually. This is just a few of them. These are some pictures of trees in Montana, and you can see that the snow just accumulates just downwind of these bands of trees. Now, I grew up in California, and the entire Sierra Nevada, California is wet or dry in any given year. So California, I joke this year is actually 2025 was extremely rare. It was actually an average year. Generally, California is either in extreme floods or extreme drought. But do the same places always have relatively more or less snow at a finer scale? So to look at this in detail, we're going to look right here in the center of California at the Tuolumne River in Yosemite National Park. And here's a picture of that in elevation. And we're just going to look at these 3 domains in different areas. This is work by Justin Flug, part of his PhD thesis. And we're going to take advantage of the Airborne Snow Observatory, ASO, which has been flying over the Tuolumne watershed since 2013. There have been more repeat flights of snow depth here than anywhere else. So this is a nice graphic from the Orange County Register in 2013. Basically, the plane flies over, sends a laser pulse, maps exactly where the ground is, flies again when the snow is there, and you get a very detailed map of snow depth. So the first thing you can look at these maps of snow depth is that 4 years have very different snow amounts near peak SWE, right? This is California, as I said, 2015, there's almost no snow. 2017, you've got places with over 4 meters of snow. But if you take each one of these years and take the distributed snow depth and divide by the domain mean snow depth, and this is following work by Vogley et al. In 2016, what you see is that these variations suddenly collapse into patterns of places that are shallow and places that are deep are very repeatable from one year to another. So again, here's 2 years with very different amounts of snow, but you can see that once we scale the factor, it's very similar. And the spatial coefficient of correlation varies from 0.8 to 0.91. So to summarize, peak snow accumulation near 1st April snow surveys and spatial patterns are repeatable across the Earth. This is why an index measurement actually indicates basin-wide water. As long as you measure at the same location each year, it's correlated to everything else in a great way. And the index measurement indicates where specifically snow is. We can also downscale or distribute based on a past high resolution measurement. And these are my grad students doing snow research up near Mount Rainier. All right, so peak snow. What about snowmelt? Are there still coherent patterns? So, so the energy balance determines when snow melts and streams rise. So we've been talking about this accumulation getting up to peak SWE. Those are similar storms at similar times. And now when that snow starts melting, this determines the onset of stream flow. And this is a function of energy balance of the snow temperature. So if you look again in the Western US, you can actually see that large rivers rise and fall at the same time. This is work by David Peterson in 2000 and by Dan Kahan in 2001. And you can see that it's pretty easy in these mountain rivers. This is for California, but the same is true across the West. Here's spring melt onset, and they all start rising at once. And so just like the music analogy we did before, I know on Zoom no one will answer me, but can anyone guess what I've got here in music-wise? This is Vivaldi's Spring. Dun, 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 dun. And if you go up in the mountains, you can hear, this is in Yosemite, the waterfalls are crashing over the sides of the cliffs, and all the water is running, and that quiet from the middle of winter is done. Spring has really taken off and made a chorus in synchrony across the West. And this synchrony can sometimes be even more than you would expect. So we know that in general, temperature decreases with elevation. So we would expect the lower elevation snow to melt first, right? So this is your average lapse rate decreasing with elevation. But in some years, the sudden warming of temperature, so this is from California in 2004, and this is weather, these are just temperature sensors at a wide variety of elevations. These are the sensor elevations in meters. But the thing to notice is that in a matter of just a few days, warming of over 12 degrees C causes everything to start melting at once. And this can be seen by, these are a whole bunch of streams at a lot of different elevations, and they're all in lockstep. Everything starts melting at once here. This is from Tuolumne, which I was showing you the data from in spring 2002. And this synchronous snowmelt, the most famous year, is actually 1983, which was following a late sequence of storms led to famously high flows on the Colorado River. If you've ever read the book Emerald Mile by Kevin Fedarko, it's talking about this river rafting down the Colorado in 1983 when they had to release huge amounts of water because there was so much snowmelt coming down. They were putting plywood up to try to keep the reservoir from overtopping and releasing as much as they possibly can. And this was in this day surrounding 22 of May, over 20 different snow-till stations started melting at once from 2,100 to 3,500 meters. And forecasts underestimated how much because they didn't think everything would start melting so rapidly. Now, the decline of the hydrograph, so we've got this onset of melt, but then the decline of the streamflow hydrograph actually depends on the snow duration across the watershed. So this part depends on snow melt and snow disappearance. And this is a picture of a salmon in the Pacific Northwest. And the reason we care so much about this is when the salmon come back up the streams. We want to make sure there's still enough water from this late season snow. So here you can see that coherently, this is the same picture I showed before of a number of mountain streams. These happen to be in California. That coherently, stream flow is shaped by the snowpack size, the duration, and the melt rates. And one thing you can see here is there are two basins here in California that are lower elevation basins. And you can see that in spring, this is March, they have runoff because they're getting spring rain with less snow right here. And the other ones are higher and they don't have any runoff at this time. So you can see right here, they're all in lockstep because they all have snow. They're all controlled by melt rates. Basically, you can see this as a synoptic systems, warm system, cold system, warm system. Now here, after June, you can actually see they start being different. And here, the duration of the stream flow is caused by the snow duration, right? These that got rain over here had less snow, and so the stream flow runs out sooner. Again, this is simple in California because after here, it's really not raining anymore. So it is a snow story. Now in late season, representing deep snow piles, this is that fine scale heterogeneity where I showed you there's certain spots that get more snow every year. This becomes actually very important in the late season. To explain this, here's a very simple model. So here's a basin with uniform snow, average depth D, basin area A right here. And over here is a basin with heterogeneous snow. It's got average depth D, but it's distributed in 2 different piles, same basin area. Our melt outflow is just going to be our melt rate times our snow covered area. So now half the snow melts. So you can see here for our uniform snow, we're now down to just half the depth. And here, one of our snow piles is gone, and we have another snow pile left. Again, we melt again. Now the snow is gone, but in your basin with a snow pile, you still have snow going and stream flow later in the season. And having this heterogeneity in your model, in whatever way you choose to represent it, is key to sustain stream flow through the summer. Deeper snow piles in shadier locations with slower melt rates last even longer. And in terms of patterns, it's a different pattern than snow accumulation, but those shady locations will be shady due to the topography year after year after year. So these late season snow piles are also repeatable patterns. Now, I promised to the people who were on early that I actually am better at predicting wildflowers than snow. And that's because snow disappearance also predicts flowers. This is Mount Rainier, and these are the flowers at Mount Rainier. This is a photo by Anna Wilson, and these are 2 papers by biology graduate students at the University of Washington looking at wildflowers. Now in terms of biology, this is an amazingly tight correlation. Snow disappearance date peak flower for these flowers here. But basically, they are just waiting for the snow to go away. And as soon as the snow is gone, all the flowers burst in the meadows. And so if you want to know when to visit Mount Rainier in the summer, take a look at when the snow is going to disappear. Now, fine-scaled maps of changing snow-covered areas can predict fine-scale maps of flower blooms. And we know where snow stays longer because of the topography, the accumulation, and energy. So here's where snow, this is a paper by Nicoletta Cristia. We know snow sits longer in these shaded depressions. And snow disappears first from steep and insulated ridges. And you can map this with great precision. And here's your late lying snow, and here's the wildflowers that just waited just for that snow to disappear and then all burst into spring. So thinking about all of those patterns and that information, do we actually know how much snow is in the mountains? So here's a picture I showed you before from Fang et al. 2023. And here's the line from the Streamflow. So we know from the Streamflow that the higher estimates here are more likely correct. These are some citations from Brian Henn's PhD thesis, where he found that many products really did not have enough precipitation or snow in the mountains. There also, I want to call your attention to a recent paper by Lawrence Mudrick and colleagues that was benchmarking snow water equivalent products across the Northern Hemisphere. And here's a list of all the products he looked at. Right here is figure 8, where he ranks all of the products. And at the end of the day, he concludes, number 1 says that mountains are harder than anywhere else, but he says that regardless, he concludes the Era 5 land, if you want to grab a current global product, performs the best. So let's look in our Western US, just take a closer look at which products will have reasonable estimates. So here you can see this is the Western US snow reanalysis product from UCLA. Purple is Snowdas, the red is the University of Arizona product, and this blue dashed line right here is Era 5 land. You also note right here in the orange that of all the GLDAS products, GLDAS VIC10 has more than the rest. So I'm going to zoom in the Western US. We'll take a look at these better products. The ones down here, we're not going to bother. They don't have enough snow. And then we'll use the GLDAS VIC as our sort of lower bound, with the knowledge that most of the other global products were significantly less in volume than that one. All right, so which products should I use? So I showed you before some repeat LiDAR maps from Tuolumne in California. The ASO has been busy. They've also been flying all of these basins all over Colorado. And here's just a picture again of what ASO does. And what I'm going to show you is some work in progress by Darren Jackson, Mimi Abel, and William Ryan Currier at NOAA in Boulder, Colorado. And we've been working together to try to say, well, okay, which products would we really recommend? And so here, this is for the Blue River. So let me just go back. I showed you the White River in Washington, and here's the Blue River right here in Colorado. And it's just an example, but the pattern holds for all of these basins. So here is the Airborne Snow Observatory. Snow, here's snow dust. Here's the Western US SWE reanalysis, University of Arizona, Era 5 land, and GLDAS VIC over here. You can see the impact of just having coarser resolution for a basin. And the benefit of having the airborne snow observatory observations is that you can actually integrate over the entire basin area and say, okay, which of these gets the snow volume correct? Whereas if we only had a snow pillow, it's hard to compare apples and oranges. All right. So based on both Streamflow and the aerial LiDAR, the highest volumes are correct. Where the mean of the set, if you just were to grab all the different reanalysis products, the mean of the set would be wrong. So here, this is taking these maps and figuring out a SWE volume. So we're basically taking the amount of snow water equivalent in each location and just summing over the area. So it's weighted by area, and it's a function of elevation. So you can see which elevations there's the most area at the spot in Colorado. And what you can see is that GLDAS VIC does not have enough snow. Era 5 land is significantly better, but also doesn't have enough snow. That ASO, which we're benchmarking as truth, has the most snow, and that the other products, the reanalysis, SNODAS, and University of Arizona, have reasonable amounts of snow. So the sneak preview, this is a paper to be submitted soon. I'm hoping the government will open so my NOAA colleagues can read the paper. This is a graphic put together by Darren Jackson. This is a graphic by Mimi Hughes. And we've expanded not just the products that I showed here, which were in the earlier studies, but also added in the University of Arizona now as an 800-meter product. There's a product by Ned Baer and colleagues called Spires that is doing backwards snow modeling. There also are more recent developments, WLDAS and CONUS 404, that have been efforts in meteorological modeling at higher resolution to better represent snow. We looked at this across multiple basins in Colorado, multiple flights in the Tuolumne in California, as well as a flight in the Olympics in Washington. One thing, this is GLDAS VIC right here. It didn't have any snow in either Tuolumne or Washington. It only had snow in Colorado. All right, so my summary, if you just want to know what snow product to use for whatever project you're working on next week, in the US in near real time, I would recommend using SNODAS or University of Arizona product. They have all performed reasonably well. If you're looking for a retrospective analysis, like patterns over past years, the UCLA SWE reanalysis had the best overall statistics. It's not available in real time, but if you are trying to find something to calibrate your weather model or something historically, I highly recommend this one. Era 5 land is still the best global product that you can get off the shelf if you need something globally. You can see that it's still in the ballpark. It has snow, at least in California and Washington. And WLDAS and CONUS 404 both have made significant improvements at getting snow accumulation, very close to right, but right now they are overestimating melt rates and timing. This is something that we can improve. We can absolutely improve the representation of melt in these models, and I expect them to only get better. I also want to emphasize that ASO never goes to Washington, and we have right now the greatest uncertainty among all the models in Washington State, so maybe we should start some more observations in my backyard. Personally, I'm biased, but I like my backyard. All right, so let's summarize this talk. It's been a very busy 41 minutes. So what can we and should we be doing right now? So what I showed you, here's the cross in Colorado. topography shapes meteorology, shapes from the precipitation to the energy available to melt the snow. Repeatable spatial patterns let us downscale coarse resolution models or map, like the snow surveys, from a point to a watershed. New technologies, such as airborne LiDAR, lets us map at very fine resolutions with high accuracy. These snow-covered area maps let us know when snow disappears. This gives us, we have finer resolution and more frequent observations from newer satellites. So one thing both the Western Snow Reanalysis and Spires Modus are using satellite observations of fractional snow-covered area to determine when snow disappears on the landscape, and they can use that to determine what snow must have been. Airborne LiDAR is mapped snow depth at meter scales. It can be useful both in the current year and for understanding the patterns that are repeatable across any year. These patterns really lend themselves to machine learning approaches, but we need to, particularly with snow data, be very careful that we are training the machines with the most accurate data available. If you grab the wrong reanalysis product, you could train your machine to come up with very wrong results. Not all snow products are created equal. And right now, if you take the mean of all available products for the Western US, that mean is wrong. Most of them are biased low. We need to be brutally honest about where and when global satellite products work well and when they do not work well. Right now, there is no dedicated snow mission, and so we need to be clever. Existing satellite sensors really only give us partial information about snow. Another path forward, given we have patterns, we also can then focus our attention on what causes our patterns to break down and how we can continue to forecast under these circumstances. So over here, this is a picture of Frank Gerke and the governor of California standing in their typical snow measurement site for that index snow measurement in April 2015 in California, and there's no snow, right? Forecasting from 0. There was still some snow on the highest peaks, but their index was gone. They had no reference to make a measurement for. Also changing signals. So this is a picture from a paper by Danny Hogan in 2024 that shows when you're looking at the precipitation anomaly and the streamflow anomaly over the upper Colorado River Basin, they tracked really well until 2000. And then since 2000, there's been less streamflow per unit precipitation measured. And the paper says it's due to changing spring precipitation patterns. And with that, I think I'm at 45 minutes, so I will stop. This is a picture of the East River Basin in Colorado, where we did lucky enough to do a field campaign a couple years ago, and the photo is by Jeremy Snyder at the Berkeley Lab, and I will stop and take questions. Thank you so much.
Thank you, Dr. Lundquist. That's a beautiful ending slide. So this is now a time when everyone can raise their hands, and I will call on you, or if you do not have a microphone, then you can go ahead and type your question in the chat, and I will read out loud. Here, I'm gonna send Melissa, I'm gonna send you an unmute request.
All right. Thanks, Kazi. Can you hear me?
Yes, we can.
All right. Thanks, Jessica. This was a super interesting talk. I guess I'm thinking about your slide where you kind of ended to say, all right, well, which product should you use where? And I'm interested to see how well CONUS 404 and WLDAS both do. And I'm not as familiar with CONUS 404, but WLDAS could assimilate SWE data. Like it you know, the list system is built that it could assimilate SWE. Do you feel like that there are, I guess I'm thinking of like commercial satellite missions that could be useful to try to pull into some of these modeling systems to help us improve, just to help us improve on some of the SWE estimates where we're currently lacking on the modeling side?
Yes, absolutely. And I'm trying to finish this paper. It goes into a lot of gnarly details, which I didn't have time to go into. But both, the one thing is that what was happening is that most of the historic products, like the GLDAS, era products never got enough snow in the first place. They did not accumulate enough snow in the mountains. They didn't have enough precipitation enhancement due to coarse resolution and not getting precip right in the mountain. Both CODIS 404 and WLDAS have really worked hard on that and made amazing improvements. And so now both getting the snow accumulation about right. Now, the next step is that what is happening, the reason they don't have peak SWE right is that they are melting the snow too early.
Okay.
I think due to errors in the energy balance. And I think what has happened is that when WRF has been developed over time, most people have targeted WRF to get precip right and to get temperature right, and have not really focused on radiation schemes in WRF. And so the long wave and short wave radiation is wrong, which is biasing the snowmelt. But there are satellite products like the Ceres product available for radiation that could be assimilated in real time or even used to bias correct the radiation in those models. And I think they're getting close. Is what I was trying to say is that there've been, these have promise. There's some products out there that I think we need to move beyond, but I think that both CONUS 404 and WLDAS have a lot of promise.
Very cool. Thank you so much.
Thank you, Justin. You should be able to unmute yourself.
Cool. Hey there. Thanks. Thanks for presenting. That was awesome. I have been thinking a lot about your comparisons you did with all the snow products, and especially like from your presentation at AG last year as well. And it makes me think a lot about all the work that's been done to date using some of these older products that we are shown to have some issues in particular. And it makes me wonder what your thoughts are on revisiting you know, all those studies. Do you think there are certain applications that are coming to potentially really, really bad conclusions because, you know, the data that they had at the time were limited to at the time were, you know, order of magnitude potentially off? And do you think there are certain applications perhaps that are less, you know, or science questions that are less dangerous to be influenced by these biases? I don't know. I'm just thinking a lot about how much to consider past research that are using these products.
I think what has been dangerous is that I'm not going to call out any particular studies, but if you do a Google search on just how well does Era 5 perform for mountain snow, you will probably come across, there's a whole family of papers that say, we looked at glob snow in the mountains, and Era 5 terribly overpredicts snow in the mountains because glob snow is based on observations from satellite, and glob snow is really low. And you can see from the more careful, well, number one, people who made glob snow masked it out in the mountain and said don't use it for the mountains. And there's a group of papers that missed that, right?
Yeah.
And then if you look at the careful analyses, it's like actually when you really look in detail, you know, Era 5 is actually doing, Era 5 land is doing the best of the global products out there right now. And if you were to make, there's some recommendations that say make Era 5 produce less snow in the mountains, that would push it in the wrong direction.
Yeah.
That's kind of my biggest concern. I feel like most people who are doing more detailed mountain studies, who have observations or looking, if you're looking at Streamflow, if you're looking at ecology, you very, with the field measurements, you very quickly threw out a lot of products. And so it's more global assessments, and I worry more about global assessment recommendations to people running global models that tell them to keep being wrong, if that makes sense. I feel like the global models could get a lot better by looking at the more regionally specific products.
Cool. All right. Thanks.
Do you have any other questions? Yeah, go ahead, Yangfei. We can't hear you yet. I see that you're unmuted. I don't know if you want to type your question in the chat. Just because I don't know if your mic is maybe having some issues. Oh yeah, that sounds good. Someone else can also ask their question while we wait for Young Fei to type. I don't mean to make us all wait for, for them. Any other questions as we wait? This is Yang Fei's question. Do you have insights on why ERA5 land performs the best in terms of estimating SWE? Do they have better precipitation or land model to accumulate snow?
So I do, and this is from plotting time series of ERA5 SWE, and it's almost another talk to go into. It gets it right by both. Well, it basically melts too slow. That makes sense because it's really coarse, right? So it's 9 kilometers, but it's downscaled from ERA5, which is 31 kilometers. And when it downscales, it doesn't actually do a whole lot of elevation adjustment in the precipitation. But for reasons that I'm not quite sure of, it has the lower elevation snow melt really slow. So I don't know, it's worth diving into more, that it seems to actually being able to get SWE about right in the mountains by, for peak SWE at least, by having something that the melt rates are just a little bit slower than they are in reality, which averages out to keep it closer to the right amount of snow. It also makes me worried about using ERA5 land as it currently is for climate studies and melt sensitivity things, because I don't think it has the melt rates right. But I also feel like more work needs to go into this before saying anything with too definitively. Don't know if that helps. I have plots of the time series that are not in this presentation, and it basically keeps snow at lower elevations around a lot longer, which then it maps, maybe the entire mountain is high elevation, which keeps it more snow. It's also an interesting lesson for like WLDAS, but if you're going to tweak the melt, tweak it maybe on the slow side.
Thank you. Do we have any other questions? We probably have time for one more. Okay. Well, in that case, thank you everyone for coming, and a big thank you to our speaker, Dr. Lundquist, for giving us this talk. Our seminar series will continue next week, and the seminar will be on our YouTube channel later on this week. So thank you all so much. Have a good rest of your day.
Thank you. Bye.
Bye-bye.